Now, we looked at x squared, but I can also look at the derivative of x to any power n that I might like, where n is some real number. And it turns out that there's actually a class, a power rule of formulas that if you have the derivative of x to the n, the answer is you take the n, which is here, you bring it down at the front, and then you subtract 1 up from the top. So for example, in the x squared that we had just seen of, where you've got a 2 at the top, the 2 comes down, but then for the n minus 1, just x by itself is really x to the power of 1, and x to the power of 1 is 2 minus 1. So indeed, what we had just seen is compatible with the power rule, but the power rule allows us to deal with any real number here. So I can, for instance, talk about what happens if I take the derivative of x to the 7/2. Well, the 7/2, it comes down, and then x to the 5/2, what's 5/2? It's 7/2 minus 1 is 5/2. 7/2 minus 2/2, so 5/2. So in other words, you get this n x to the n minus 1 behavior as well. Now, I'm not going to prove the power rule, but it's a similar idea to what we had just seen. We could use the definition of the derivative and a bunch of funky algebra to try to move in the direction of proving this power rule. Okay, so what if I don't have just powers, but I have like some sums of powers? In other words, I've got a polynomial and I want to take the derivative of a polynomial. How can we deal with that? Now, what I notice is that this is the derivative of the sum of a bunch of things. So I kind of want to ask a broader question. What is the derivative of the sum of two things? And indeed, the claim is going to be that the derivative of a sum is going to be the sum of two different derivatives. Notice I've got a derivative of f plus g, and I say it's the derivative of f plus the derivative of g. So this is a rule that allows us to quickly solve the derivative of sums if I know each individual derivative. So we want to prove this, and we're going to prove this by the definition of the derivative. So I'm going to begin with the left-hand side here. So what I'm claiming, I'm dealing with this, the derivative of the sum, and what I'm doing is the definition of the derivative. So the definition is the limit as h goes to 0 of whatever I have at x plus h minus whatever I have at x, all divided out by h. It's just that the thing I'm taking the derivative of is now f plus g. So when I'm taking my derivative of this, that what I get is f plus g at the value of x plus h minus f plus g at the value of x, and then all divided out by h. So now after I've applied the definition of the derivative, I want to do a little bit of algebra. So I'm going to take these components, and I'm going to take the f of x, and I'm going to combine them together. So it's going to look like this. All I've done is rearrangement. I've put the two yellow, the things with f together. I put the two blue, the things with g together. All right, now what can I do? Notice that this is the limit of a sum. And we've previously had a rule for the limit of a sum. The limit of a sum is the sum of two different limits. So what I can do is take this, and I can break it up here as the sum of two different things. But then I know what the thing on the left is. Limit as h goes to 0, f of x plus h minus f of x all over h. This is the definition of the derivative of f. And then the same process over here, that's the definition of the derivative of g. And so that I'm going to say that this is equal to the derivative of f plus the derivative of g. Now, I should add as a caveat that as we've gone through this process, what we need to have is that both of these limits exist. Indeed, you might have recalled that the limit of a sum was the sum of the limits. I could distribute a limit through a sum, that is, but that only worked if those limits were defined. So this additivity property, it's true the derivative of the sum is the sum of the derivatives if both of those two derivatives individually exist. Next up, we have a very similar result, scalar multiplication. The derivative of a constant times f of x is a constant times the derivative of f, that I can rearrange where the constant goes. Now, if we wanted to, we could do a proper definition of the derivative like we had just done for additivity, but I'm going to show this to you graphically. So what I'm going to have is a graph. I've got some function f of x here, and then I have a different function which is twice f of x. So in other words, I've got a c value of 2. Now, remember, a derivative represents the slope of the tangent line. But for straight lines, the tangent line and the function, they're just right on top of each other. So a tangent line and the function are the same thing. Okay, so how are the slopes of these things related? Remember, a slope is a rise over a run. Well, if we look at the f, we could compute the rise over the run here. But if I look at twice f of x, notice what happens here. So this is the slope for twice f of x. The run here is the same. But the rise, that has doubled because it's gone from whatever the height of f of x was to twice that. So alternating between those, we've got a rise over a run, and then we have twice the rise over the same run. In other words, what we're going to have is that the slope of 2f of x is exactly twice the slope of f of x. And this is an illustration geometrically of this scalar multiplication rule. All right, so back to this polynomial that we're trying to figure out. We've decided that yes, we can deal with sums, and yes, we can deal with multiplication by scalars like this 3 that's hanging out here. So my first step is to apply additivity. I say the derivative of this polynomial is going to be the sum of 3 different things. The first term, the second term, and the third term, where we're taking these derivatives of each individual term. That's additivity applied multiple times. And then the next thing I'm going to note is that if I have this 3 times x, well, the derivative of the 3 times x is just 3 times the derivative of x. Derivative of x by the power rule is just 1. Likewise, x cubed, I can apply the power rule to that. And derivative of a constant, we know that that's 0. So applying each of these derivatives, what I'm going to get is 3x squared, so that was the power rule. Then scalar multiplication rule together with the fact that x to the 1 goes to 1x to the 0, and x to the 0 is just 1. So that's another way of putting it. The 3 and the derivative of a constant is just going to be 0. So a derivative of a polynomial is actually pretty quick and easy after you get the hang of it. You just sort of do it term by term, applying the power rule as needed, and multiplying by whatever scalars you might have out the front, in this case, the 3.